So hi everyone, and welcome to the second part of the lecture on the basics of deep learning. So now that we've seen some of the elements of a neural network, so let's see how we can train the network and how we can use it to do some cool stuff like classify images and segment images. So the first thing we'll see is how to train the network. So when you want to train the network, which basically means to learn the parameters of the network using some training examples, there are actually two steps that we need to carry out. The first step is the forward pass, where we're going to take each of the training examples. We're going to augment each example with basically our bias. And then we're going to pass the example through the network to generate the output and compute a loss. So to generate the output, so in the case of this network, what we're going to do is we're going to multiply our input by the weight matrix of the first layer, which is W0. And then we're going to apply our activation function, which could be a sigmoid, for example. Then we're going to do the same in the second layer. So we're going to multiply the result by a weight matrix W1, augment this result with a bias. And then in the last layer, we're going to multiply by a weight vector W and get the output with a final activation in the output layer. So why do we use a vector here instead of a matrix? Well, it's simply because in this case, we assume that it's a two-class classification problem. So we want the output to be a single scalar, okay? So this is why we have a vector. So if we had multiple outputs, for example, for a K-class classification, then we would also have a matrix here, but this matrix would have as many rows as we have classes. Okay, so as I mentioned, the next step is to compute a loss function, which will measure the error or the difference between the predicted value, which is y of x, and the target value, which is t. Okay, so as we saw, a typical loss function that we can use for binary two-class classification is binary cross entropy, as shown below. Right. So to optimize the network, there are a couple of things that we need to do. So the first thing is we need to define our loss function that we are minimizing. So our loss function is composed of two different things. So the first thing is a sum of errors or losses on each of our training examples. And typically here, we can actually average this over our n examples. And then we also want to add regularization function R, which is applied on the weights, the parameters of our network. And as we mentioned before, this term is used to avoid or to minimize overfitting. So there are many ways to choose the regularization function. Two very common choices is the L1 norm and the L2 norm. So the main difference between the L1 norm and the L2 norm is that in the L1 norm, typically what happens is we're going to have matrices that are sparse. So what that means is that if we use this norm, then there's a good chance that a lot of the weights will be close to zero. And this is almost equivalent to basically disconnecting or having a sparse connectivity pattern in our network. Okay, second thing we have to choose. So once we chose the regularization function, we have to choose the loss function. And that really depends on the type of problem. In the case of classification, A very common choice is the cross entropy. So the reason why this is a good choice is basically because it leads to a fast convergence. It also has some nice, it's also grounded on some very nice mathematical notions, as we saw before. And of course, depending on the loss function that we'll choose, then we have to adjust the output layer of our network. Okay, so for example, if we use a cross entropy, so cross entropy assumes that the output is a distribution, and therefore to obtain a distribution, we have to use either the sigmoid in a two-class problem, or the softmax in the more general K-class classification problem. Okay, so the third step, which is I guess the more important one for this lecture, is computing the gradient of the loss with respect to each of the parameters, right? Because basically the optimization is based on gradient descent. And in gradient descent, what we do is we take the current value of each parameter, and we're going to make a little step, which is opposite to the gradient, right? So how do we compute the gradient? So the gradient is just the derivative of our total loss function, which is this. Again, we can divide the first term by by n, so multiply by 1 over n. So it's going to be the derivative of this function with respect to each of the weights of our network. Okay, so given this gradient, so what we're going to do is we're going to take the current value of each parameter, and we are going to subtract the value of the gradient. So here, this is a scalar because the weight is also a scalar. And so this is what we call the step. And the size of a step, so the size of the change that we're going to do to this parameter, is going to be proportional to our learning rate eta. So this is the learning rate. Okay, so basically this is the gradient descent algorithm. And what we do is we're going to repeat this process several times until we converge to a solution which is a local minima. Okay, but the main question here is, how do we do this efficiently, right? So the problem is that the loss function is a value which is computed here, but what we want to do is we want to compute the gradient with respect to a parameter which can be anywhere in the network, including in the very first layer, right? And that is where the backpropagation algorithm comes in. So again, let's illustrate this with a simple example where we have an input of size 2. We have 2 hidden layers in our network, and we have an output layer for a 2-class classification problem. So basically, the output of this last layer is a scalar, okay? And here, we're going to use the standard binary cross entropy as our loss function. Okay, so to explain things, let's give a name to the network, so the output of the networks at each layer. Okay, so the output of the first layer, we're going to call it A. So this is right before the activation. So if we apply the activation to the output of the neurons, we get B. And then if we multiply B by the weight matrix in the first layer, we get C. And then applying the activation on C, we get D. Applying the weight of the output layer, we get E, which is a scalar. And then finally, to get the final output, we apply the activation on E. Okay, so this is basically the exact same function as we had before, but we just gave some symbols or variable names to each of the steps of this computing process. Okay, of course, we have the loss function at the end, which, as we said, was binary cross entropy. All right, so again, the main problem here, the main issue is how do we compute the derivative of the loss? So notice here that I removed the regularization term just to make things a little bit simpler. So how do we compute this with respect to any weight matrix, including the weights of maybe the very first layer of our network? And to do this, what we need is called the chain rule. So what is the chain rule? So the chain rule is basically a way to compute derivatives of a composite function. So let's give an example here where we have a function f, which takes as parameter u, and u is itself a function of v, and v is itself a function of x. Okay, so the idea is that f depends on u, u depends on v, and v depends on x. So the question is, how do we compute the derivative, for example, of function f, with respect not only to u, but also to v and to x? Right? So for example, what is the derivative of f with respect to x? And notice here that this symbol here, this symbol refers to the partial derivative. So it means that if we have a function which depends on many different variables, the partial derivative is the derivative with respect to only one of these variables. So in this case, it's actually quite simple because we have x, which affects v, which affects u, which affects f. So if we want to compute the derivative of f with respect to x, we have to follow the chain rule. And what does the chain rule say? It says that the derivative of f with respect to x is the derivative of f with respect to u times the derivative of u with respect to v times the derivative of v with respect to x. Okay, and that sort of makes sense because, as you can see, these terms cancel out, these terms cancel out, and what we get at the end is the derivative of f with respect to x. Okay, so if we look at each of these terms individually, so it's actually quite easy to compute them because we have, it's basically just regular functions that we can differentiate. And we're simply going to multiply each of these derivatives to obtain the final answer. Okay, so the final answer, which is the derivative of f with respect to x. Okay, so let's go back to our network. Again, what we want to do is compute the derivative of the loss function with respect to the weights in one of the layers. So for example, the weights in the very first layer. Okay, and it's the exact same thing as before. Okay, so we're going to compute the derivative of the loss with respect to the output. So the output is what we have directly here, times the derivative of the output with respect to what's right before the output, so E, and then the derivative of E with respect to D, and so on and so forth until we get to W0. Okay, notice that here, once we have computed all this, so we're now at A, so all we have to do is derive A with respect to W0, and then we're going to get what we're looking for. Okay, so why is this important? Well, this is important because it actually took quite some time to get to this, this algorithm. Even though we had the mathematical tools to do such calculus, nobody had actually implemented this, and it took some time. And the reason why is this important because it makes training the network actually quite efficient. And in fact, it's important to realize that the backpropagation phase, which is how you compute the derivative with respect to any parameter, starting from the end to the beginning, is as efficient as the forward propagation pass. So imagine propagating the information from the input to the output is actually quite efficient. Well, this algorithm allows us to do the reverse just as efficiently. So how does it work? Well, the idea is quite simple, right? Is that we are going to backpropagate the gradient starting from the gradient with respect to the output. And then we're going to use this information to compute the gradient of the loss with respect to E, right? So notice that this will be used to compute this. And in the same way, we're going to reuse the gradients at the previous step. So the gradients for the layer, which is closer to the output, backwards and backwards and backwards. Okay, so the fact that we are reusing the gradient of the following layer to compute the gradient at the previous layer is what makes this algorithm actually quite efficient. All right. So of course, the backpropagation is a little bit more technical than that. So we haven't talked in the details about how we differentiate the different operations. But that's not very important because, in fact, if you use a standard deep learning library like PyTorch or TensorFlow, these are actually done automatically for you. So let's talk now about activation function, which are a major component of neural networks, and in particular in deep learning. So the activation function that we saw for logistic regression is the sigmoid, right? So the sigmoid that you can actually see here, and this is the definition of the sigmoid. So that was actually the very first activation function that was proposed, because this is actually a soft version of the threshold function, which is at the basis, which is used as at the core of the perceptron. And the perceptron were the first neural network models that were proposed. Okay, so it sort of made sense to have this kind of differentiable version of the threshold function. And so for a long time, this was the function that was used in almost all the neural networks. But this activation function suffers from three very important problems. So the main problem of this function is that if we look at the gradient of the sigmoid, So the gradient is actually the slope of the function, right? So here we have a slope of 1. So the gradient is 1. Well, the problem is that if we are in this position, so for example, if the input of the sigmoid is big, or if, so big meaning a big positive value, or if we have a large negative value, so we see that the slope of this function is almost 0. So in fact, it goes all the way to 0 as the input goes to infinity or minus infinity. And this is very problematic because it means that the gradient, if the input of the function is either very big or very small, it means that the gradient will be close to 0. In a very shallow network, that's not such a big issue. But what happens in deep learning, as you can see here, let me go back a little bit. What happens is that you multiply a gradient, the gradient at a given layer, by the gradient at the previous layer, by the gradient at the previous layer, and so on and so forth. So if this value is very small, so let's say very close to 0, and the same for this value, and the same for this value, and all of them, what's going to happen is that very quickly, with very few layers, you're going to have a gradient that's going to vanish. And that's what we call the vanishing gradient problem. And for a long time, this problem made it almost impossible to train networks that had a large number of layers. Okay, so this is a major, major problem. Another problem, which is, I guess, somewhat less significant, is that the function is not zero-centered. In fact, you can see that it's centered at 0.5. And this makes sense if we want to have a probability, right? Probability ranges from 0 to 1. But from an optimization point of view, this is a little bit problematic because it means that we're going to have some sort of bias in the activation of the neurons. And so it might generate some sort of, of course, we have the bias to correct this problem, but let's say we didn't have the bias, what would happen is that the values might actually, shift toward, there's going to be a bias toward positive values, right? We're never going to have negative values, or it's going to be harder to get negative values. Third and last problem is that if you look at the function here, well, it requires to compute an exponential function, and exponential function is actually quite expensive, although you can approximate it very efficiently. But if you want to have a high precision, then it's actually expensive compared to, for example, a multiplication or subtraction or etc. Okay, so another very common function is the hyperbolic tangent, which has a very similar shape as the sigmoid function. The main difference being that instead of ranging from 0 to 1, the hyperbolic tangent ranges from -1 to +1. So now we have an activation function which has a 0-centered output, right? So that's interesting because the values can be both positive or negative, and we're not going to have like this kind of biasing effect. But it suffers from the same vanishing gradient problem because as we have an input value which is either large positive or large negative, then again, our gradient will be close to 0. Right, so how do we address this issue of the vanishing gradient problem? Well, there's this very simple and elegant function that we can use, which is called the ReLU. You probably have heard of it. So ReLU stands for rectified linear unit. And this function is actually very simple. So if the input of this function is negative, for example, here, the output of the function will be 0. So it's going to be a constant, and the constant will be 0. And if the input is positive, then the output will simply be the same as the input, right? So it's a linear function which has a slope of 1. Okay, so mathematically, how do we write this function? Well, it's actually very simple. We can write it as max of between the max between 0 and x, where x is the input of the function. And that's actually quite easy to see, because if the input is negative, right, the maximum between a negative value and 0 will be 0. This is what we see here. Otherwise, the output will simply be x itself. Okay, so this is quite interesting. So that was actually, it's a very simple and very simple modification, but that actually made things much, much easier to train networks. Why? Well, because here, for x greater than 0, so we have a non-saturating function, which has a non-zero gradient. So you can notice that the gradient here is always equal to 1, regardless of how far we are from 0. So that's the first thing. So that efficiently solves the vanishing gradient problem. Another advantage is that it's super fast, because notice that here, we don't have expensive operations like the exponential, right? So it's just a max, so a simple comparison between a value and 0. That's it. Well, actually, just testing if a value is negative or not. Okay, however, the output is not centered at 0. Again, this is a very minor problem. But perhaps the greatest problem here is that there is no gradient when x is less than 0. Okay. It's actually worse than that, because the output will be 0. Okay, and what's happening, the main problem of this is that once, for example, let's say that we have a neuron with a ReLU. So what's going to happen is that once you give a negative value, let's say x less than 0, so the output of this function will be 0, and the gradient of this function will be 0. So what's going to happen is that this neuron will be effectively a dead neuron, at least for this particular training examples. So there's not going to be any way of changing the output of this neuron, because it always outputs 0, and its gradient is 0, meaning that you will never be able to change its output. Okay. And if this is the case for all the training samples, then what's going to happen is basically the network will completely ignore this neuron. Okay, so this is called the dying neuron problem. So how can we solve this last problem? Well, there are several ways of doing it. One very interesting solution is called the Leaky ReLU. So the Leaky ReLU is a small modification of the ReLU, where instead of computing the max between 0 and x, you compute the max between a small factor times x and x itself. Okay, so what does that mean? Well, it basically means that if x is positive, so x, remember, x is the input. So if x is positive, then you're going to have exactly the same as the ReLU function. So you're going to have a line with a slope of 1. But if x is negative, instead of having a flat line or a constant value of 0, then you're going to have another line, another linear function, but this time with a much, much smaller slope. Okay. So again, we have a nonlinear function because even though it's composed of two different lines, there is a break here. So that makes the activation function nonlinear, which is very, very important for training networks that have several layers. But you can notice that the gradient will never be zero unless, unless you are exactly at this position, but that rarely happens in practice, okay? So we have non-saturating gradient. We solve the problem of a dying neuron as well. And we also have a super fast function because, as before, we have very simple operations. Okay, the only, I guess, small inconvenient, and in practice it's rarely an issue, is that the slope in the negative portion of the input is a hyperparameter. It's typically fixed to 0.01. That usually works quite well. But nevertheless, this is a hyperparameter, which might not be optimal in all scenarios. So the last activation function that I want to show you, again, is a small improvement over the Leaky ReLU, and it's called the parametric ReLU. And the only difference here is that this constant is replaced by a hyperparameter, which is itself learned during training, okay? So what that means is that we let the optimization determine what is the best slope for the negative portion of the input. All right. So in practice, what do we do? So we saw several options. In practice, most people nowadays, when I say most people, I mean most architectures, and for most application, will use the ReLU. Why do we use the ReLU? It's simply because it works pretty well in most cases. And although there is this dying neuron problem, this problem does not happen that often because of stochastic optimization and because of batch optimization. So there's always a chance, because we're not constantly showing the same examples when we compute the gradient. So there's always a chance that there's going to be one or at least one example that's not going to have a zero output or a zero gradient, and therefore this example might actually, help have a non-zero gradient. Nevertheless, in several cases, in fact, many times, you can get a better performance using a Leaky ReLU or a parametric ReLU. So you might want to try this to get a better performance. In some cases, very rarely, you can also get maybe an interesting performance with the hyperbolic tangents. In my experience, the hyperbolic tangent is usually used at the output of the network for situation where, let's say you want to do some sort of a robotic control, and you want to predict an angle. So let's say you have a driving car, and you can steer the car at a specific angle, right? So an angle of 0 means you keep going straight, and then let's say minus 20 degrees is you turn left 20 degrees, plus 20 degrees, you turn right 20 degrees. Well, as you can see here, the output, the possible output is a value which is centered on 0, and that can be both negative and positive with symmetric maximum values. And this is, in this kind of problem, actually hyperbolic tangent makes a lot of sense, right? Because that's exactly what you want to predict. So you just need to take the output of your hyperbolic tangent and multiply it by the maximum value. And you're going to get a range of, let's say, minus 20 to plus 20. centered at 0. Okay, but nevertheless, if that's not the case, then you're better off with a ReLU or a Leaky ReLU or parametric ReLU. And a sigmoid, well, again, sigmoid is rarely used nowadays, except at the output of the network, if you are doing a two-class classification, right? Because a sigmoid, the output of a sigmoid is between 0 and 1. So that's actually quite convenient to model a probability. And when we do classification, typically the output of a network is a probability. Okay. In the case of a two-class classification problem, the probability would be the probability of one of the two classes, the one that you want. It doesn't matter because the probability of the other class is simply 1 minus the probability of the first class. Okay, so moving on. Now we're going to talk about classifying, we're going to talk about classifying specific things. And because this is a lecture about, or I should say, a school on medical imaging. So we're going to talk more specifically about how to classify images. So an image, as you all know, is simply 2D array of pixels. And here we're going to consider pixels as simple intensity, so grayscale values. So we have a single scalar per pixel, which measures the gray level. And let's take a very simple example of a digit, which is represented as a matrix or a 2D array of 28 pixels by 28 pixels. So that gives a total of 784 pixels. Okay. So of course, when we look at this image, all of us can see, the number 8. It's actually not very difficult for humans to recognize simple symbols or simple objects as this. But what does a computer see? So what a computer sees is the actual values, right? So the actual numerical values that represent the intensity of pixels. And so it's actually a little bit harder, to make sense of this information. So what we're going to see is how do we convert? So how do we use this information to do classifications? Basically determine. So given that the input is an image or this 2D array of numbers, how do we get the label corresponding to the number? In this case, the label is the number 8. Okay, so if we use multi-layer perceptron, so MLP, so this basically the type of network that we've seen so far. So the standard approach would be to take this image and then to consider, or in fact, this image like this, so with the numbers, and then to consider each of the pixels, so each of the 784 pixel, okay, as a different input to the network. So we're basically, you can think of it as converting this 2D array into a 1D vector. And then we're going to add, of course, the bias to this vector. So that's going to give us 785 inputs. And then we're simply going to, compute the output the exact same way as we have done before. So by connecting, every neuron on the input layer with every neuron on the second layer, which is our hidden layer, and then every neuron of this layer to the output layer. And here the output layer is composed of 10 different neurons because we have 10 classes, right? So digits go from 0 to 9, so that's 10 classes. All right. So how many parameters do we have, right? So the parameters are the weights of the connections in the network, right? So here we have, again, 785 neurons in the input, right here. In this particular example, we have 10 neurons in the hidden layer. So this is just an arbitrary choice. We could have used more or less. Although in this layer, the number of neurons is fixed. It's determined by the problem. So the total number of connections between the input layer and the hidden layer is going to be 785 times 10, which is 7,850 connections. So that's 7,850 parameters that we need to learn. Okay. So 7,850 parameters is not that much. Okay, when you think about it, nowadays we have, we have some architectures, some network architectures that have, hundreds of millions of parameters. So this is actually not so hard. Okay, what I mean by not so hard is like you can actually learn this even though you don't have that many training samples. But what if we have a more interesting image? So an image that has a size of 256 by 256. So for example, what if we have a brain MRI, brain MR image? Okay. Well, now we have 65,536 pixels. Okay, so that's if you take 256 by 256, you get 65,536. You're going to add the bias. Okay, so you're going to add an extra neuron for the bias. And again, so that's going to give you 65,537 neurons in the input layer. Again, you have 10 neurons in the hidden layer. So the number of parameters is going to be this times 10, and that's going to be 655,370 parameters. Okay, and now it's starting to be quite big. Okay, and in fact, let's say you want to train the network to classify MR images. Well, chances are you're not going to have so many training images, right? So we all know that getting medical images is complicated, especially if we need to have labels, so manual annotations of those images. So even in a favorable case scenario, we might, best case scenario, we're going to have maybe 1,000, 2,000 images to do the training, sometimes much less than that. So learning that many parameters with only, let's say, 1,000 training images is just impossible, in the sense that what you're going to do is you're going to overfit your data in a major way. And the problem is even worse if you consider a volumetric data. So, for example, you have MRI that can have 256 slices if you have a very good resolution. And then that's just doomed to failure because you have 16 million pixels, and then that means roughly 160 million parameters, and that's only in layer 1. Okay. So basically, what this means is that a multi-layer perceptron, which is fully connected, for which every neuron in one layer is connected to every neuron in the following layer and the previous layer, is not going to work for large images, or even less for 3D images. So what can we do for this? Right? So what we can do is that instead of considering a fully connected network, so instead of considering that every neuron is connected to every neuron in the next layer, right? So again, just to introduce what follows, I'll give you another example. So imagine that we have an input that has 150 values, so 150 dimensions in the input. And let's say that we have the same number of neurons in the first layer. So that's going to be 100 times 100 parameters, which is 20,500 parameters. Okay, again, if the two layers are fully connected. So what can we do instead? Well, what we can do is just reduce the number of connections. So for example, instead of saying that this neuron is connected to all the neurons in the previous layer, we can say that it's connected to only 3 neurons of the previous layer. And the position of the neurons to which it is connected is, I guess, in this case, related to its position, right? So, for example, this one will be connected to the 3 neurons here. The next one, which will be blue, is connected to the next 3 nodes. And then the following one, which is green, will be connected to the following 3 nodes, etc. Okay, so we introduce a local pattern of connectivity between the 2 layers. And now, because each, sorry, let me clear that. So because each neuron is only connected to 3 neurons in the previous layer, the total number of connection between these 2 layers is 150 times 3, which is 450. Okay. So we went from 22,500 parameters to only 450 parameters. Okay, so that's quite a big step. But the question is, can we do better? Can we actually reduce the number of connections to less than 450? And again, we could do it by simply removing all the connections, but the important thing is we want to preserve this kind of local connectivity between a neuron in this layer with neurons in the previous layer. Well, there is a solution, and that solution is to simply share the weights. So what does that mean? It means that we keep the same connections between the neurons. So this neuron is still connected to the same neurons. This neuron is still connected to the same neurons. So each neuron is connected to 3 neurons. But the difference now is that what we're going to do is we're going to share the weights across these different connectivity patterns, right? So each neuron has 3 connections with the previous layer. So there's 3 different weights. And we're going to simply constrain these weights to be the same, whether it's here, 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 or actually anywhere in between these 2 layers. Okay. When we go to another position, so I'm sorry, when we go to another layer, then we're going to have different sets of weights, but at a specific position in the network, so between 2 specific layers, the weights will be shared. Okay, so to summarize, we have this fixed local connectivity pattern, which is the same at different position. And we have the same weights shared at different position. And the thing is, if we have these 2 constraints, what we get is, in fact, a simple convolution. Okay, so the operation of computing the value for each neuron in this layer from the values of the neurons in this layer is simply, in this case, applying a 1D convolution. So we're going to consider these weights as a convolution filter of size 3, and we're going to move, it's as if we're moving this convolution filter along the weights of the first layer to generate the output at the second layer. Okay, so I'm going to explain this a little bit more into the detail in the coming slides, but I just wanted to make the link between this very compact architecture, which has local connectivity and shared weights and convolution. Okay, so again, so the learning of these weights will now be equivalent to learning convolution filters, because we're applying convolution operations. And because the number of parameters is actually quite small, so in fact here, if you look at the actual number of parameters required to define the connections between the first layer and the second layer, well, it's only 3, right? Because regardless at where we're computing the output, we're always going to use the same 3 weights. So we went from 22,500 to 450, and now we're down to 3. Okay, it's quite a jump. So because we have so few parameters, okay, it means that we can actually have networks that are very deep, okay, because there's less danger of overfitting our training data. Okay, so just to illustrate this one more time with an example. So imagine that our input is composed of these values. This is for one single example. So these could be anything. It's really not important. Just think of it as a vector of real numbers. And then let's assume these values for our 3 weights. So this is basically the values of our convolutional filter. So what we're going to do is we're going to apply a convolutional operation, which means that at every position, we're simply going to multiply each connected neuron with its corresponding weight. So we're going to multiply 2.3 with minus 0.1, 1.7 with 0.2, etc. Okay. This is what we have here. And then we're going to apply our activation function. In this case, we used a sigmoid, just for the example. And we're going to get the final output of our neuron at this layer. Okay, for the next neuron, it's exactly the same thing. So notice that the weights haven't changed, right? Because it's the same convolution weights. And again until we reach the end. Okay, and this is, as I mentioned, this is a convolution. So let's look at it now on an image, on an actual 2D image. So now our filter is also a 2D array. Okay, so for example, it could be a 3x3 convolution filter, right? Which has 9 weights or 9 parameters. And we're going to apply this filter at different positions. In fact, at every possible position of the image. So we're going to apply this, we're going to apply this, we're going to apply this. And in the end, what we're going to get is what we call a feature map. So a feature map is basically the result of applying a specific convolution filter to an input image and applying our activation function. And a feature map is an image. So the input is an image and the output is also going to be an image, which is going to have the same dimension as the input image, except that it might be a little bit smaller due to the fact that, for example, if I want to apply a 3x3 convolution, for example here, so notice that the first place that I can apply this 3x3 convolution is not going to be at the top left pixel, but rather at this pixel here. Oops, sorry. Rather at this pixel here. And so because of that, I will lose a little bit of the border of the image. Okay, I will lose a little bit of the border of the image, unless there's a way of solving this, which is to pad, which is to do padding and pad the original input image with a small border. In this case, it would be a border of 1 pixel. And that will allow me to apply my convolution. Okay, sorry for my drawing. But it's going to allow me to apply my convolution at the right position. Okay. And I think the next talk will spend a little bit more time on these details, so I'm not gonna insist on that. But important thing is to know that the output of a convolutional layer is also an image, right? It's not an image which is in the same space as the input image, but it's an image, and the content of an image is what we call a feature map. Okay. Of course, one feature map is interesting, but it's not enough to capture all the characteristics of an image. So typically what we're going to do is, in a convolution layer, we're going to apply several convolution filters. For example, here we have 1, 2, 3, 4, 5 different filters. Okay, each of these filters will be for example, a 3x3 convolution filter. So it's going to have 9 parameters each. And each of them will produce, so at the output of that first convolution layer, it's going to produce a different feature map. Right? So in this case, we're going to have 5 different feature maps. And we can consider the total output of the layer as an image, if you want, that has almost the same dimension as the input. As I mentioned, it might change if we have padding or not. But the number of channels is the number of convolution filters that we applied. Okay, so how can you, an interesting way of picturing the channel is like, for example, if you have a color image, typically a color image is encoded as a RGB. So an RGB image has 3 channels. Well, you can think of the output of this convolution layer as another image, which has 5 different channels. Okay, so what are these channels representing? That's really depending on the application, and sometimes it's actually very hard to understand because that's something that the network is learning by itself, and we don't really have any information on the semantics. Okay, so this is just a summary. So again, we have an image. We're going to apply, okay, a convolution filter at different position. At a specific position, we're going to get a single value, okay, for one filter. And then applying the same filter across the different positions of that image will give us one single feature map. And then if we do the same thing for another filter, for example, a filter green, then we're going to get, okay, another feature map at the output. Right, so of course, we're going to do this at not only at the first layer, but at different layers. And what's going to happen is that we're going to transform the input gradually in the network until we get to the output. But the one problem is that, imagine that we want to do classification, right? So in classification, what we want to have is a single, let's say in the 2-class classification, we want to have a single scalar at the output, which will represent the class label, or the probability of a given class, right? So how do we go from a 2D image to a single value using only convolution operations? Well, it's not really possible. So in order to go from an image to a scalar, we need to basically reduce the size gradually, the size of the features, until we get to this, this single value or single vector. And the way to do this is to use a pooling layer. So what is a pooling layer? So a pooling layer is a little bit like you can think of it almost like a convolution operation, except there's 2 differences. One difference is that in some cases, for example, in the case of a max pooling, instead of applying a weighted sum, like in a convolution where we multiply with a weight and then we sum all the values, we're going to apply a function which basically, well, in the case of a max, we're going to look at the maximum value within that window. Okay, so it's a way of aggregating the values, but it can be something else than the weighted sum. Okay, so look at this example. So here we're going to use a 2x2 pooling size. And what that means is that we're going to consider sub-regions in our image or our feature map, which have a size of 2x2. And then within each of these regions, we're going to take the maximum value. Okay, so for the green region, the maximum is 100. So the output of the pooling layer at this position will be 100. For the red region, the maximum is 184. So we're going to have an output of 184. Here we're going to have 12, and here we're going to have 45. Okay, so that's the first difference, is that we can have other functions, like for example, the max, which is typically pooling layer have a max function. And another thing is that because we want to reduce the size, typically what we're going to have is non-overlapping windows. So in a convolution, right, I would take my window here, and I would simply shift it by 1 pixel to the right to get this window here. But in the case of a pooling, we want to have the output, which typically we want to have the output which has a smaller resolution as the input. So what we're going to do is we're going to shift our window in such a way that the two windows are not overlapping. And this corresponds to doing a stride. So the stride is the displacement that we do of the window. So in order to do this, we're going to have a stride which is the same as the size of the window. So if we have a 2x2 pooling region or pooling size, then we're going to have a stride of 2. If we had a 3x3 pooling, we would have a stride of 3. Okay. This is not exclusive to pooling layers, so we can also have stride in convolution. But again, that's a topic that will be presented in the next talk, so I'm not going to go too much in the details. Okay, so as I mentioned, max pooling is very commonly used, but there are other types of pooling. Another type of pooling which is often used is average pooling. And in average pooling, we simply take the output in a region or in a window as the average between all the values in that window. So for example, here 36 is the average between 31, 15, 0, and 100. All right, so why do we use pooling, right? So as I said, pooling is necessary in classification networks because we basically need to reduce the size in order to get a single value at the end. But there are other reasons to do it. One reason is because we want to lower the memory and computation requirements. When you think about it, if I go back a little bit, so the output, even though the number of parameters is small, the output of a convolutional layer is going to be the same as the size of the input times the number of filters that we have, so the number of channels, right? And if your image is large, or imagine that you have a 3D volume, a 3D image, so volumetric data, then multiplied by the number of channels, that can be quite big. Okay, so, and because we do all these operations in a GPU, graphic card, and the amount of memory in a GPU is actually quite limited. Nowadays you can have GPUs that have several gigabytes of memory, but still that's quite a limitation when you have large images and if you want to have large training batches, for example. So this will lower the memory and computation requirements because you're going to gradually reduce the size of your feature maps. Another interesting property of this is mostly in the max pooling is that it provides some invariance to translation, scale, and rotation. So what does that mean? So it means that if I give you an image of an 8, of the number 8, and then I give you an image of the same 8, but slightly shifted to the right, to the left, it doesn't really matter in which direction. The output of the network is not going to change so much if you have a max pooling, because if you consider just, I'm going to use a bigger pooling window. But my point is that even though you shift your image a little bit, the maximum value within that window and within that window is very likely going to be the same, right? Because the maximum value within a group is not so sensitive to adding a column or removing a column. It's the chances that the maximum value will be within that shifted column is much less. In the same way, it provides a little bit of invariance to scale and rotation, although this is, you cannot like completely rotate your 8. It's like a very slight rotation. Right, so this is a typical convolutional network. So in a typical network, you're going to alternate between convolution layer and pooling layer, convolutional layer, pooling layer. Sometimes you can have several convolutional layers between a pooling layer. It really depends on the architecture. But the idea is to alternate between these two types of layers. So let's say you want to do classification. So at some point, you will need to take the output of typically of a pooling layer. And suppose that now your output has a resolution of 1. So, I mean, you've downsampled your initial image often enough that what you get is a single element. So if you want a single pixel, but you can have a large number of channels. Okay, so here we have a large spatial resolution, but we only have a single channel, okay, because it's a grayscale image. And at the very last pooling layer, we have a very low spatial resolution. Typically, it could be a 1 by 1, but we have a large number of channels, for example, 1024 channels. And the point I want to make is that this becomes a vector. Okay, it's simply a vector. It's a vector of 1024 elements. And then what do we do? Well, we take this vector and then we just consider the rest of our network, which will take this vector and output, a class probability or the probability of several classes in the case of a K-class classification. We're just going to define the remaining layers of the network as fully connected layers, just as we had done initially. Okay, how many fully connected layers do we need? Well, typically not so many, because we assume that this will generate a good representation vector. So typically we can have 1, maybe 2, maybe 3, but rarely more than that. Let's say 1 to 3 layers at the end, and then we have our output. Okay, so this is for two-class CNN. So we have a single scalar at the end. Here we have the binary cross-entropy function. In the case of K-class classification, well, we simply apply the softmax. We're going to have as many outputs as we have classes, and then the cross entropy. So cross entropy will change. It's not exactly like this. Okay, so now we're going to sum over the different classes. So it's going to be something like this. Okay, so K-class cross entropy is almost the same as this one, except we have to sum over the classes now. Okay, so I'm almost at the end of the talk. I'm just going to give you some examples. So very quickly, so this is an example from the literature where we have basically we want to have an input MR image which has it's actually a single image of size 96 by 96, but it has 4 channels. The 4 channels correspond to 4 MRI sequences. I believe it's T1, T1 contrast, T2, and the T2 flare, something like that. And then we have 2 convolutional layers followed by a pooling layer. So notice that the pooling layer will divide the resolution by 2. So instead of a 92 by 92, we're going to have a 46 by 46, followed by 2 other convolution layers, followed by another pooling. And then here we have, I believe it's 2 fully connected layers. So this is simply converting this into a vector. It's called basically a flatten. Flatten is the operation of taking whatever you have at some point, which is, we call it a tensor because it's in 3D, and we just flatten that into a single vector. And then we have 2 fully connected layers, and then we have a softmax, and we have our probabilities of the 2 classes. In this case is whether the image is of a healthy patient or whether the image has a tumor, a brain tumor, that is. Right, so what is the network learning? Well, again, this is going to be covered in more details, so I'm not going to spend too much time, but essentially what we learn in the first layers of the network are very simple features representing edges and, for example, blobs. And then as we move on to the end of the network, we're going to learn information which has much more semantic content, right? So let's say we learn a network to classify or to recognize people. What we're going to find is that the very last layers are going to model basically the different types of faces that we can find. Batch processing. So batch processing is just a way of, instead of passing a single example to the network to compute a single output. So what we're going to do, so for example, this is a single example, we get the output, and then a second example, and we get the output. So in batch processing or mini batch processing, what we're going to do is we're going to combine 2 or more examples in a single set, which we call a batch. And then we're going to run all these examples at the same time in the network to get as many outputs as we have examples. Okay, So here we have 4. So this is a batch of 4. So there are 2 reasons why we want to do this. The main reason is that we want to make all these computations in parallel. So, with a GPU, it's much more efficient to compute. So when we do the forward and the backward, we do it for all the examples in the batch instead of one example at a time. The second reason is that when we compute the gradient, we want to actually compute the gradient over all the examples in a batch instead of computing the gradient of one example and then doing the gradient step, another example, gradient step. What we do is we compute the gradient for all example, we average these gradients, and then we do the step on this average gradient, or the sum of the gradients if you want. Okay, so again, here we want to do object, so image classification. We have a batch of 4, so we have 4 different predictions. And just to close this this second lecture, so I will just give you very briefly examples of common problems that we find in image analysis and, of course, in the medical imaging as well. So the first type of problem is classification. So classification, as you know, the input is an image and the output is a class. So the class could be either the class of the object in the image, or in medical imaging, it could be, for example, if a patient is healthy or not. So here are several examples of classification. And the second type of problem is image segmentation. So image segmentation is also a classification problem, but instead of predicting a label for the whole image, for example, healthy subject or not, what we do is we predict a label at every position of the image. Okay, so, and this is basically equivalent to dividing the input image into different regions. Okay, one of which can be background and the others which could be, for example, some different anatomical region in the image. Okay, so this is cardiac segmentation, where we want to segment the left and right ventricle. This is bones, bone and cartilage segmentation. This is a brain tumor segmentation. And the last problem is called localization. So in localization, it's a little bit different. It's a little bit similar to segmentation, but different in a sense that we are given an image, but instead of predicting the class at every pixel, what we want to do is we want to detect some possible objects in the image. And on top of that, we want to be able to predict where these objects are in the image. Like, for example, if we do pedestrian detection from a surveillance camera, well, first of all, we don't even know how many pedestrians there are, right? So we want to identify how many of them there are in the image, and it could be, in some cases, there could be none. And second thing is we want to predict the position of each of those pedestrians that we detected. And the position is typically given with a bounding box, okay? This is basically on the right. So we basically have an example of car detection where we want to find the cars, and we also want to track them as they move to give their speed, for example, their velocity. Okay, translating this into a medical imaging application, well, we could have, for example, tumor localization. Okay, again, this is very similar to segmentation. The main difference is that, for example, if there are 2 different lesions in a brain, segmentation would say, well, this is part of the lesion class, if you want. So pixels that are here or here are labeled as a lesion. Whereas localization would say, well, this is a lesion. I detected one lesion here, but I also detected a lesion here. And these two lesions are separate. Okay, so that's the main difference between the two problems. Okay, well, that concludes my lecture. So I hope you enjoyed it and you learned some new things, and I'll be taking your questions now. Thank you.